So, two more presentations. First one under the title, Software That Writes Software. This is where I start, as a mere mortal, start to get feeling particularly nervous, but delighted that we're joined by Dr. Gerard Gorman, reader in computational science at the Department of Earth Science and Engineering in the Faculty of Engineering at Imperial. So great to have you with us, and you're going to be looking about this auto-generation area. So I won't say any more to give the maximum time for you to share some of the research you're involved with.
Thank you. It was a week or two ago I gave a variation of this talk, and one of the people asked me afterwards, says, "Oh, what's going to happen when the robots start writing software for themselves and kill us all?" And I said, well, that'll solve our worry that automation will take all our jobs away. But I think what you'll see is that it's a lot more practical than this. So what I want to get across at the beginning is the scale of the problem that we're trying to solve and have a good motivating problem. Like, you know, what exactly we're trying to do here. So, like off the coast of Brazil, like in 2006, they discovered what they call the Lula oil field. It's estimated to have tens of billions of barrels of oil. So that's kind of revenue that can pay the bills for a country the size of Brazil. It lies about 250 kilometers off the coast of Rio de Janeiro. It's under 2 kilometers of ocean and then 5 kilometers of salt, sand, and rock. So this is not the kind of thing that you just happen to stumble upon. So what do they do in the practice and industry? Well, like the ships are sent out to do surveys. And to give you an idea of the scale of that, say everyone talks about big data. So like I like to talk about, okay, this is what real big data is. So like Polaris is one big company that does this type of work. And they had a press release last year talking about one survey that they did, where they have a ship pulling an array that's 2 kilometers wide and 10 kilometers long. At the time, it was the largest sea construction that had been built and pulled by a single vessel. And it's the largest man-made moving object on the planet. So it's quite big. Then taking another example, again on numbers, just moving on to the data. So what's that doing? That's pulling a whole bunch of sensors that are effectively microphones. So CGG is another big company that deals in this, and I just pulled off some other numbers of what a typical survey was, how much data were they collecting anyway. So for a single survey, this is some data I pulled off for 2014. A single survey in the Gulf of Mexico was 1.5 petabytes. That doesn't include the fact that when they're taking the data off the ship, they're contractually required to have 4 copies of that. So quite a lot of data. Now, when you have a lot of that data, you have to get from what is ostensibly just a bunch of wiggles, because you're just sort of listening to the sound, to actually creating like a 3D image, sort of like a tomography that you might have in hospital, to build up an accurate image of what it is that's actually down there in the subsurface. So because of the data, it's an incredibly complex problem. And like that typically takes anywhere between 9 and 12 months to build up that image. And that's using, what I think is quite fascinating here, is that as far as I'm aware, this application, the largest supercomputers in the private sector are to solve this problem. So it really is big in all aspects. Now, the kicker is that to send a ship out then, if you know no more than your radiologist, like, you know, looking at a blurry image, that's effectively what they're looking at, is a blurry image. They say, okay, well, I interpret this image. I think, well, that kind of looks like it might be oil. To send a ship out. If it's in a region that, like, you know, that you already have the infrastructure there, you already have a bunch of ships and everything else, then, like, the cost of drilling an exploratory hole, like exploratory surgery, exploratory hole, see if, like, you know, if they got it right, there's something down there, costs about 20 million. If it's in a whole new area, it's 200 million. And if it's a new area, the success rate is about 10 to 15%. Like, so 10 to 15% of the exploratory holes actually found something. So you're looking at, like, you know, vast, like, and they are just like being a bit confused about whether that blurry thing might be interesting or not. Like, you know, that's potentially going to cost you 200 million. So obviously, like, people want to stop wasting that kind of money. So, like, where can we innovate? How can we improve this? There's clearly a very large inefficiency in it. Well, for a start, you're going to get better images. You want to collect more data and better quality of data. Of course, like, you're already suffering because, like, it's quite difficult to deal with the volume of data that you're getting, and the volume of data that you want to collect is basically exploding. There's always better algorithms. Like, at the moment, what they say, full waveform inversion, like FWI, it's basically a machine learning problem. Like, it put in popular terms, control optimization problem. And like that's constantly being improved upon and made better, trying to get a more accurate image and be more efficient. But also the software technologies. Like, here you're talking about software that requires expertise, like mathematicians, geophysicists, people that know about data management, people that know about, like, software engineering, people that know about, oh yes, and then you have to rewrite all of that really complex software for multiple different architectures. So that wouldn't be a big deal. You say, well, it's oil and gas companies. Like, this is potentially going to save them like billions. Like, can't they just throw money at it? But you also have to take into account that IT projects are absolutely notorious for massive failures. Like, think about the 10 billion write-off from the NHS IT project. I don't know, it could be 10, it could be 20. It seems to change every year when they reassess it. It's a big number, okay? So we have to reflect why that happens as well. So typically for these types of problems, like, that's normally then where, like, our team, like, comes in. So, like myself, I've got about 20 years experience in terms of taking very large, horrible, like, ugly, like, engineering and science codes and trying to modernize it and make it go fast on supercomputers. And this is across a whole range of applications, from like CFD, ocean modeling, like nuclear engineering, and so on. And one of the reasons why HPC is seen to be, like, HPC is really seen to be a specialist task even among, like, hardcore computing people. And the reason is because you're effectively trying to hire people who are specialists in everything, because there's a whole bunch of maths in there. There's difficult calculus that hurts people's heads thinking about. You have the domain expertise because you have, like, all the details associated with that particular application. And then they have to figure out, like, then as Joe was pointing out, like, say you might code at a high level, but really then to get performance, like, remember here, you're talking about, like, computing something on a supercomputer that takes 12 months. Okay, you really need to get that down. Specialists actually really need to know where's each bit and byte going on the machine and really squeeze the maximum performance out of this. So it gets extremely complicated. And the fact is that there's very few polymaths out there. And like, what's even more depressing is, like, we all know we want to do new algorithms, and, like, algorithms are the key. Like, those who, like, develop algorithms are going to, like, control the future. But even to do the most trivial change or trivial improvement to your algorithms and your numerics, you're looking at getting this, like, polymath, and basically facing into maybe 6, 12, 24 months effort to change a few 100,000 lines of Fortran. And, like, frankly, like, most intelligent people have better things to do than making the similar tedious changes to hundreds and thousands of lines of code. So, like, and it's because of that, and it's because I spent, like, nearly my entire career doing that kind of work. Like, I think that it's just, like, frankly, it's just, like, reckless and misleading and silly to think that we're going to generate a whole workforce of people who are able to do this. Because, like, if that's the amount of work that you have to do, and now there's several other new computer architectures and you have to keep redoing it, you're not going to train that workforce, period. You have to start thinking about how you're going to do things differently. So largely, I think the way that we're doing things is just not fit for purpose. Like, say, I think that the status quo has been great for, like, people like my groups, because, like, people give us research contracts to do loads of stuff for them. But as I tried to highlight, like, it is actually tedious and it's not sustainable, and it's ultimately bad for everyone. Okay, it's bad for us because we're doing boring work, but it's bad for everyone in industry and everything else, because this is why, like, maybe we don't see as much innovation as we're expecting to see out of HPC. This is why we're not always seeing the value that we might expect out of HPC. Like, why aren't we, like, why don't I have a little try tricorder and things like this, like they do in Star Trek. Like largely it's because there's a whole bunch of smart people who have got all the mathematical skills and insights and physical insights and everything else. They're spending all of their time editing a few million lines of legacy Fortran, and that's the reality. So, like going back in a second, like it was interesting because I've done so many of these projects, and then it was a couple of years ago, it was a BG that contacted me saying, okay, we know you're the HPC guy, can you talk to the geophysicist? We want to do something in seismic. And then we got introduced to Joe at Intel and said, okay, can we collaborate and do something on this? And I was there, well, the last thing that I want and the last thing that we're going to do is have another pimp my style, like, HPC project where we're going to take someone else's got off the code and just make it go fast. We've done that lots and lots of times. But it's just like we want to do something a lot more disruptive. Like rather than just taking one bespoke code and pimping it, as it were, like say, how are we actually going to like fundamentally change how people address a whole field or a whole class of problems? So, like, this is nearly like a retrospective history now, because after we did a lot of research, I went back and tried to understand it in a historical context. And what I was really fascinated by is back in the 1950s, there was like one of the big hot subjects, big hot topics that people had, like those conferences and everything on this, it was like everyone was really excited about, was this thing called automatic programming. And what it was, it's like, so this started up, so in 1952, it was Grace Jones had the first, developed the first compiler, like A0. By 1957, like IBM had released like the first version of the Fortran compiler. And interesting, it was the first version. The big problem that they had with introducing a compiler, because largely everyone else was actually doing machine code, and then like Fortran was introduced and said, no, we don't like this high-level thing that makes our life easy. We want to continue writing machine code because it's really fast and we get the most out of the machine. And they didn't really care that they had to rewrite the same code on each separate computer. Like, it had to be done differently. And it was only in 57, that's also why they called it the first optimizing compiler, because it was only at that point, like IBM, flogged themselves to death to get a compiler that could actually just, beat for a large class problems, like what people were doing in machine code. And then things quickly changed on from there. But I think largely, it's been a pity that that term, automatic programming, was lost, because I think it really informs us, how we should be thinking about programming, the problems they face then and going forward. So this made a big impression on me, because now when we program in C or CUDA or OpenCL, to be honest, when I go to a HPC conference, I hate hearing about a new parallel paradigm, because what that means in practice for the people that actually do real work is writing another million lines of code in some other god-awful language on a different machine. But the parallels between this experience today and the 1950s, you have to admit, is striking. So this is where, so often a niche in computer science, since the 1950s, there has been people working on what's called domain-specific languages, where, so COBOL is one of the classic examples that's used as a first example, where people say, well, let's continue on this trick, and let's start developing a language that's bespoke to an application. So again, it's not robots are going to use this, start taking over the world. The idea of a domain-specific language is you said, okay, this is the domain of applicability. It's going to do this one thing, it's going to do very well, and then we're going to implement stuff around this. And then it's going to plug into integrated with other software. So how you design these, and then you write compilers. So what actually a compiler is something that reads code that's at one level of abstraction, and then optimizes it, improves it, and writes it out at a lower level of abstraction. That's how it's defined. So we write compilers then to do exactly this. So in our case, for example, so here's this, in this, this is when you work with corporate partnerships to address your slides, keep changing everything. But so largely what we can get away with then is where that the human or your application developer only writes 3 or 4 lines of equations, and they actually write equations in symbolic Python, symbolic maths in Python. Our compiler then takes that and says, okay, look, we know it's finite differences. We know exactly all the rules about finite differences. We can look up the textbook. We know exactly the umpteen different ways that people have of parallelizing this. And we can integrate it with other tools, and it does all of that legwork for you. Oh, and the nice thing as well, going back for a second before I've got scary academic-looking results, is like in contrast. So we have this working. We're like using it with seismic codes. Like other people that we know that are doing this in traditional ways with their Fortran codes and whatnot, like they have like codes that go on for a few 100,000 lines of Fortran. We're doing all of this and more, and we've got 3,000 lines of Python. Like say we're just 25 months into our project in collaboration with Intel. We've already completely rewritten all of our compiler and all of the technology as our understanding developed and matured 3 times. Okay, we can do that because actually we can throw our code away and start again with based on new understanding. That's what application codes in science and engineering cannot do today, and it's what's murdering them. So I don't know how I managed to sneak this slide in. Like, it's got actual results. Okay, so like some of the technical people here will recognize this, but for the people that don't, effectively the top line there that looks like a roof line, so that tells you like for a particular chip, what's the maximum possible performance that could be extracted out of this, okay? As in, the machine doesn't go any faster. Like, it's not a perfect model, there's lots and lots of caveats, but anyway, that's a whole other story. And then the blue dot then is the performance you're actually achieving. So this is a really neat tool then that you, like, rather than making like relativistic type comparisons of performance, you have something absolute. You can start saying some definite things. It's not like politics. So in this case, so this is like 2 examples. One is on a new Xeon processor. The other one is on a Xeon Phi. And so on the Xeon processor, we're reaching 20% of peak performance. And then on the Xeon Phi, 10 to 20% peak performance. Now I look over nervously at Joe as he said, well, that looks a bit rubbish. So now here's the kicker. So normally when these types of application projects are done in collaboration with computer scientists and that, typically what's done is that they throw a simple version of the problem over the fence to them. They cut it up, they get some nice academic papers. But then like none of it is actually useful in the real application. So in this particular case, people tend to look at simple acoustic, like, equations. And it's nice, there's only a few terms, you can make it go really fast and it will sit on the, like you get your students to do it, it'll sit on the roof line. Now, but that's not what we're doing here. Here we're actually solving what's called TTI, so this is basically what industry typically would use. In both of those graphs, the point that is on your left-hand side, that's like, a 4th order version of it. So the equation that's being executed there, that's been evaluated everywhere, has got 2,000 terms. As you get to 16th order on the right-hand side, it's up on 6,000 terms are in the equation. The point here is actually, frankly, I don't care that we've reached 20% or whether it's 30%. Frankly, it doesn't matter. The fact is that like only a small number of teams in the first places have the resources and expertise to be able to implement anything that's on the left-hand side. Humans simply start failing because of the complexity involved in implementing stuff to the right, on the other side. Now, the other interesting part of this, before I get the hook get pulled off, is when this was done, it was with Matthias, so one of our collaborators visited us. And he said, okay, we want you to implement TTI because like various people were asking, want to see some serious results. So he got a bunch of papers, each which had a different way of implementing it, academic papers, about 5 or 6 of them, I forget how many. In a single afternoon, he implemented them all, evaluated them all, identified that more than half of the implementations were just not usable because they were numerically unstable, they had to be chucked. Identified the ones that were good. Of the ones that were good for the forward model that weren't actually useful remember we were talking about machine learning type algorithms here, so there's a bunch of details where you need some bunch of other stuff. So most of the other algorithms also didn't work with it for those extra features you needed, which basically boiled down to 1. That was all done in an afternoon. Normally just one of those dots, that would be like, 6 months, 12 months, depending on how good the programmer is, just to implement one of these things, just to implement one of those ideas. And this is what's done in the afternoon. So frankly, the whole point about performance is, we're rewriting again. That dot will make its way up. We're meeting one of Joe's ninja developers like over in Atlanta next week, where we'll work through some of the performance problems to get it up to the roof line. But I don't think that's the big story. The big story is that we're making humans productive, and that's our most valuable resource. The future is wonderful, and there's no killer robots. I think basically automatic programming is seriously disruptive. I think we're really sort of reaching the tipping point as well. Like it was just an email that I got from Joe recently that just said, all technology follows the same pattern. From genesis, customization, standardization, commoditization. And I think if you look at the Gordon Bell Prize from last year, 3 of the finalists, to a lesser or greater degree, were using code generation technology. So I think we're pretty much at the point of going from customization into standardization with this. And I think, okay, it's always for foresight, we're supposed to be looking 10 years or further, but every time we try to look in the future, it seems to move towards us at an alarming rate. But I think because we are actually making the process of programming itself programmatic, I think what I'm particularly excited about is the potential to start introducing AI and machine learning into the algorithm discovery process itself. And that's going to be fun. Thank you.